In the last video, we talked about how temperature affects solubility. So in this video, we're going to talk about a way that we represent that, which is using solubility curves. So a solubility curve is really just a visual representation of that relationship between temperature and solubility. So this just represents or shows how the solubility of a substance changes with temperature. So we said that different substances were affected differently, specifically talking about whether the solute is a solid or a gas. So this is an example of several solubility curves all plotted on the same axes. So you can see that different substances have very different solubilities, and different substances are affected very differently by temperature as well. So first, you should notice that most of our curves go upwards as temperature increases. So the x-axis down the bottom is temperature in degrees Celsius. And this is dissolving in water. So the x-axis is given for the entire range where water is a liquid from 0 to 100 degrees Celsius. And then our y-axis is grams of solute per 100 grams of water. So this is a little bit different than molarity, which we've been using. It's how much solute to how much water to how much solvent specifically. And we can see that the effects of temperature are very different depending upon the substance. We talked in the previous video how if a solute is a solid, it generally increases in solubility as temperature increases. So we have quite a few solids here. We have Ki, NaNO3, potassium nitrate, ammonium chloride, potassium chloride, sodium chloride, and potassium chlorate. So those are the ones where the curve goes up as the temperature goes up. And you'll notice that they're very different. So something like sodium chloride is this brown line here, barely changes at all. It starts out at maybe 37 grams of solute per 100 grams of water and gets up to 40, barely changes as you increase the temperature. But then we have something on the opposite end of the spectrum here, like potassium nitrate, that starts out really, really low and then it skyrockets as the temperature goes up. So some solutes aren't affected that much by temperature, like sodium chloride. Some solutes are affected a lot, like potassium nitrate, and then we of course have everything in between. We also have some gases represented here. Hydrochloric acid, ammonia, and sulfur dioxide all have curves that go down as temperature increases, meaning that they get less soluble as the temperature goes up, which is characteristic of gases. So this is a visual way to see how the temperature affects the solubility. And if we think about what this really represents, these curves, the lines themselves, represent a saturated solution at every temperature. So any point that is directly on the curve represents a saturated solution, meaning that that is the most solute we can dissolve in 100 grams of water at that temperature. That, for instance, let's pick something that's a good number. Right about here, this is NH4Cl is ammonium chloride. We can dissolve 60 grams of ammonium chloride in 100 grams of water at 70 degrees Celsius, and that would be a saturated solution. That's the most we can put in at that temperature. At other temperatures that would vary, but that's what the curves really represent, is the maximum amount that can be dissolved under those conditions. Anything underneath the curve would represent an unsaturated solution. That is less than the maximum. So if we tried to dissolve those same 60 grams of ammonium chloride at 90 degrees Celsius, we'd be over here, which is underneath the curve that we were looking at for ammonium chloride. So that means if we dissolved 60 grams of ammonium chloride in 100 grams of water at 90 degrees Celsius, we're creating an unsaturated solution because we could put more in if we wanted to. Anything above the curve is generally going to be impossible. Under very, very rare circumstances, can you create a supersaturated solution? But you should not ever really assume that that is going to be the case. If we tried to dissolve, again, we'll stick with the same example, 60 grams of ammonium chloride at 40 degrees Celsius. Now our ammonium chloride curve is down here. We're trying to put 60 grams in, but we can't. We're above the maximum, so we're not going to be able to dissolve it all under those conditions. Again, supersaturated solutions, super weird, not the norm. You have to go out of your way to create one. It doesn't just happen. So it's important, if you're looking at a solubility curve, to recognize what the areas under, on, and above the curves really mean. Keeping in mind that the curve itself is saturation, underneath is unsaturation, above you're generally not going to be able to dissolve that much. So these types of curves are really useful in helping you determine how to make a saturated solution if that's something you want. What is the maximum? Or can I create a solution that's as concentrated as I want? Or is it impossible? Am I trying to dissolve too much stuff? So keeping in mind that the y-axis here is grams of solute per 100 grams of water always. We can read information off the graph that will allow us to figure out how we can make a saturated solution. We can use this data in a number of different ways, really. So let's do how much ammonium chloride is required to create a saturated solution in 500 grams of water at, let's do 30 degrees Celsius. So if we look at our graph, we're still using ammonium chloride. So we're looking at this curve right here. The temperature that we're interested in is 30 degrees Celsius. So we want to look at this curve at 30 degrees Celsius. It's here. We follow that up. We find that we are right about 40, maybe a little bit higher. I'd probably call it 41 grams when we read over to our y-axis. So that to me looks like it's just a little bit above 40 on the curve. You're eyeballing it off a graph. If you don't agree with me, that's fine. I would call it 41. If you're doing something like this where you're reading a graph, there is always a little bit of wiggle room allowed in your visual estimation. So what the graph is telling us is that at 30 degrees Celsius, I can dissolve 41 grams of ammonium chloride in 100 grams of water. So the problem here asks us about doing this in 500 grams of water. So there are a couple different ways that you can think about this. First is that the ratio is going to stay the same. So the idea of concentration is really a ratio of amount of solute to amount of solvent in this case. So we can say if 41 grams of ammonium chloride can dissolve in 100 grams, then X grams of ammonium chloride can dissolve in 500 grams of water, because that ratio is going to stay constant. A saturated solution at 30 degrees Celsius is going to have the same concentration overall, so that ratio of solute to solvent is going to stay the same. So then we can just solve for X here, which will be 41 grams of ammonium chloride over 100 grams of water times 500 grams of water, which gets us 205 grams of ammonium chloride. So the other way you can think about it is essentially if 41 grams can go into 100 grams of water, I'm using 5 times as much water, I can dissolve 5 times as much stuff. So either way we'll arrive at the same answer. For things that aren't nice integers like that, it's nice to be able to set it up this way. But that's the general idea. So we can always use this to figure out how much can go into a saturated solution. Am I able to dissolve as much as I want is another way to look at it, that if I want to dissolve 300 grams into this solution, that's not going to be possible at 30 degrees Celsius, maybe at a higher temperature, but not under these conditions.